the chat box, which is on your right, and to just say demo or something like that. As well, while you're at it, you can use the chat box to put in any questions that you have during the webinar. I may not be able to answer them during the webinar as I'm talking. However, I will come back at the Q&A period at the end of the webinar to review all of the questions. So at C-Therm, we're really about making thermal conductivity faster, easier, and more accessible to users and to scientists from a wide variety of application fields and backgrounds. The goal is to make it fast, easy, and repeatable. We have a number of thermal conductivity instruments. That's kind of our bread and butter here at C-Therm. The one on the far left-hand side of the slide is really our budget option for groups that are really either budget constrained or they like to have the freedom to kind of build their own thermal conductivity instrument. So if that sounds like something that describes you, you can take a look at the TC kit. On the far right of the slide, you can see the TX Touch Experience platform. That's our thermal effusivity platform for application in the textiles industry. We won't be talking too much about that one today. Most of the work that we're looking at today is in the instrument that you see in the center of the screen, the Trident thermal conductivity instrument. It offers 3 methods of thermal conductivity testing. ASTM D7984 or the modified transient plane source method, ASTM standards D5334 and 5930 for the transient line source sensor, and ISO 22007-2, which is the standard that governs application of the transient plane source sensor that you see on the left-hand side of that pyramid in the background, the sensor with the yellow part on it. And the reason why we offer 3 methods with our Trident thermal conductivity instrument is really that one of the things we've noticed in the industry is that people will tend to use the tool that they've got, regardless of whether or not that tool is necessarily the best fit for the samples that they're working with. So, for example, if all you have is a MTPS sensor, you might be trying to shoehorn that sensor technique into situations where it's not the best option out there. So the idea behind Trident was to give the user more options to pick and choose from so that they can pick the technique that really is the best fit for the scenario. And what it boils down to is this quote from Abraham Maslow: when all you have is a hammer, everything looks like a nail. The idea being that, you know, if you only have the one tool, you're going to try and make it work, even if it's not necessarily the best option. So the sensors offered with Trident, you can see on this slide. The modified transient plane source sensor is visible on the left-hand side of the slide. You can see the active area of the sensor in the center of the top of the illustrated sensor. And that active area is approximately 18 millimeters in diameter. On the right-hand side, you can see the transient line source or needle probe, TLS sensor. which has a needle region of 150 millimeters or 15 centimeters long. It's really best for things like unconsolidated solids, gravels, tars, and sticky materials like polymer melts. And then in the bottom of the slide, you see the transient plane source, or TPS sensor. That sensor, or that test method, comes with the option to choose from multiple sensor sizes and pick and choose the sensor size that is appropriate to your application and to your sample. We offer a number of accessories with our system. You can see on the upper left-hand side the liquid cell for the modified transient plane source, or MTPS method. On the upper right-hand side, you can see the high pressure cell, again for the modified transient plane source method. This one is often used to test liquids above their normal boiling point, and also to test solids under elevated pressures when the application would make sense. On the lower left, you can see the liquid cell in action for testing a fluid. And then on the lower right, you can see the compression test accessory for controlling the compressive force applied to samples. On this slide, you can see some of our TPS module accessories. On the upper left is the sample clamp, which we recommend for ensuring a good, consistent clamping pressure when you're running a test. On the upper right, you can see the 3 different sensor sizes that are available as standard. On the lower left, you can see the high temperature 300 degrees TPS sensor in Kapton. There is also an option to get a sensor very similar in appearance to that one that can go up to 500 degrees Celsius at this point. And then on the lower right, you can see the TPS powders testing accessory. We also have, now that we've talked a bit about the methods, it helps to have some guidance on which method to choose when. And so that's kind of the thing that was the reason behind us creating our method selection guide. So the method selection guide is a document that I helped co-author along with some other colleagues here at C-Therm. And it basically reviews some of the common transient methods of thermal conductivity testing that are available and helps to provide guidance on which method to choose when. If you would like to take a look at the method selection guide, it's free for anyone to read. Rosa will be putting a link in the chat box. Thank you, Rosa. And you can click on that link and it will take you to the method selection guide page. For each of the techniques, there's a different range of thermal conductivity and temperature operating range, as well as different precision specifications and standardized testing methods. So this kind of gives you a summary of the options in terms of their thermal conductivity capabilities and their temperature ranges. We also collaborate in North America with a couple of partners. The more recent one is a group called Metroviv. This group is one that we have recently started distributing in North America. They're a world leader in dynamic mechanical analysis testing, so we don't have a whole lot of DMA content this week. It just didn't make sense. But if DMA is of interest to you and to your applications, please note that in the chat box. We'll get somebody to we'll get our MetroVib representative to reach out to you. Below that, you'll see a group by the name of C-Therm. C-Therm is a brand of the KEP Technologies group, and they really specialize in very high performance, extreme environment, high precision thermal analysis equipment, including things like TGAs, simultaneous thermal analyzers, DSCs, as well as some more sophisticated and specialized calorimetry techniques like Tian-Calvé calorimetry and adiabatic calorimetry. So if any of those options sound like they would fit a need for your group, and either now or in the near future, please note that in the chat box. We'll get Cameron to reach out to you up here if you're up here in Canada, or we'll put you in touch with the C-Therm representative for your region. We can talk about ourselves all day, but what's really important is what our clients have to say about us. So I'm going to highlight a couple of testimonials, and you can, if you'd like to see more of what our clients have to say, Rosa can put in a link to our testimonials page. The first one is from Dr. Enrique Jackson at NASA. He says, we purchased the C-Therm TCI thermal conductivity analyzer after seeing a demonstration of how fast and easy it is to operate. The instrument provides unequivocal results and provides the flexibility to test powders and liquids. In terms of our satisfaction with the purchase, I'd give it a 10 out of 10, extremely satisfied. The second one is from Stuart Sykes at Haydale Composites. And he says the C-Therm TCI has been a key piece of testing equipment at Haydale, providing fast and accurate thermal conductivity measurements for our product development of nanocomposites. Having this capability has allowed a better understanding of the dispersion of nanomaterials in polymer matrices through thermal mapping of sample surfaces. The support and customer service from C-Therm has been excellent over the years, and we look forward to dealing with them again in the near future. So that's the words of two of our clients who we appreciate very much that they allowed us to share those. So with that briefing on the Trident thermal conductivity instrument and its capabilities out of the way, we'll take a look at the technical content for today's talk. So really, this is looking at heat transfer fluids and lubricants, specifically with an eye toward application in electrical vehicle systems. So electrical vehicles generally operate off of batteries in most cases, and so when you cycle the battery, that is going to generate some level of heat. And the heat needs to be managed so that the battery does not overheat past its ideal operating temperature range, and definitely not past its self-accelerating decomposition temperature range. So the important thing here is to make sure that we are managing the heat that is generated and spreading it where it needs, away from the source of the heat, so that the most temperature sensitive components in the device cannot get overheated and potentially fail. When you're looking at thermal management in the context of electric vehicles, there's a couple of key design metrics that you need to keep in mind. The first one is thermal conductivity. Thermal conductivity is the most important thermal property for the application of thermal management to heat sinks, electrode materials, construction materials, as well as the lubricants, because most of the lubricants tend to be quite viscous. So the heat is transferred more by conduction than it is by convection in most cases. The other one that can be important for some applications is the specific heat capacity. And that is particularly important when you're looking at things like heat transfer fluids and other coolant fluids, as well as when you're looking at the certain transient heat transfer considerations where the heat capacity will dictate how quickly the heat can spread throughout the material. It will dictate the thermal diffusivity of the fluid. The other thing that is a key design metric in the context of electrical vehicles and anything where you're dealing with batteries is the thermal stability of the battery assembly and different components within the electric vehicle. The thermal stability is going to govern the thermal runaway behavior, and when you get to a point of unstoppable thermal runaway, which can lead to fires in some cases. In other cases, it can also lead to minor explosions in batteries. So obviously, that's something we want to much. So keeping the temperature at or below the maximum operating temperature of the battery is key. So for electric vehicles and vehicles in general, you end up testing a lot of liquids and a lot of fluids. And when you're testing fluids, it's really important to make sure that the behavior that you're measuring is the behavior that you think you're measuring. By which I mean, we can we see a lot of work in the literature. It's not the majority of the work in the literature, but there are literally hundreds of thousands of papers published every year talking about the thermal conductivity of different fluids that are being developed. And if you take a small percentage of many thousands, it's still a lot of papers where the testing conditions being employed are really going to encourage the onset of a different type of heat transfer called convection. So convection is heat transfer through physical motion of a fluid or material. So most often in end user applications, you can observe it if you have a steaming hot cup of coffee and you can watch the steam flow up from your coffee cup. That's kind of a natural convection in action. Or if it's so not this time of year, but if you have a hot summer day and you want to stand in front of the air conditioning unit so that you'll cool off, that's a case of forced convection in a consumer goods setting. Convection is a good thing for most thermal management applications. Gases and fluids transfer heat very well through their heat capacity when you're moving the fluid. So in most thermal management applications, things are designed to encourage efficient convection over surfaces that are either generating heat or which are basically acting as heat sinks to spread the heat away from the heat source. In the context of measuring thermal conductivity, however, convection is a real challenge because instruments that measure thermal conductivity are really measuring heat transfer and then inferring the thermal conductivity from the heat transfer behavior. So if you have this second method by which heat can be transferred other than the thermal conductivity that at play, then you're going to overestimate the expected or the thermal conductivity if you're taking a measurement at a condition where convection is going to be occurring. On the other hand, thermal conductivity, which is what we're wanting to look at in this context of metrology, that's the transfer of heat energy through a material from one particle to the next. It can be through the electrons in an ionic or metallic material, or it can be through phonon transfers where physical molecules are actually vibrating and bouncing into each other and back. So as an example, if you've got an aluminum pan, I'm sure I'm not the only one who has picked up an aluminum or cast iron pan and immediately let it go and said a few choice words. So if you've ever had that experience, you've understood the danger of thermal conduction, or rather the effect of thermal conduction would be a better way of saying that. So I've talked a bit about the difference between the convection, which is where the fluid is physically moving, and the motion of the fluid is allowing it to transfer heat through its heat capacity. And I've talked about the difference between that and thermal conduction, where the heat is just transferring through a stationary or static material from one molecule to the next. So how do we make sure that we don't have convection and ensure that we have a lot of thermal conduction? So for that, there's three main principles that you need to keep in mind. The first one is that you want to reduce the volume requirements of the fluid sample for measurement. What that does basically is it increases the amount of friction that the fluid is experiencing because it's in contact with the wall of the vessel that you're using to contain it. And by increasing the friction, you discourage the onset of convection. So basically, you're using the fluid's viscosity to your own advantage. The second one is that you want to employ a short duration test, typically 1 second or less. This is because convection is a physical process, and it's largely a process driven by the onset of a density gradient in the fluid, where the less dense material, which is in contact with the heat source, is going to want to rise up because of the force from the more dense fluid material from cooler regions of the fluid. So if you have a short duration test, I mentioned viscosity before. The viscosity will kind of help to inhibit the onset of convection at first. And if your test is very short, you can start and finish the test before the fluid has time to react to the force that is being generated by the thermal expansion of the fluid near the heat source. The third one is to reduce that force by employing a very low energy heat pulse. So you don't want to have a large amount of heat being pumped into this fluid, because that's going to increase your buoyancy forces and encourage the onset of the convection. You want to have a very low energy heat pulse to kind of discourage the onset of the convection. So most of the work, actually, I think all of the work I'm talking about today is collected using the modified transient plane source test method. It is the method we recommend on Trident for testing fluids because of the very short test time offered by this sensor of less than 1 second. So one of the things that it's important to do whenever you're looking at making a test method for testing liquids is you want to validate that the method does not have that convection error that I was speaking about before. And one of the ways that we can do that in terms of increasing our confidence that the performance of the method is going to be good is through the use of numerical simulations. So this was some work generated a few years ago, simulating the onset of convection during an extended heating pulse on a MTPS sensor. In this case, it's water being simulated. But when this work was conducted, there were other fluids that were simulated as well, including acetone and methanol. So you can see after 1 second, there's no evidence of convection. The heat profile is very flat and uniform across the surface of the sensor. By 5 seconds, same sort of thing. The heat profile is still very flat and uniform. But by 11 seconds, we have some evidence of convection, where you have the isothermal lines on the plot become a little bit arched. And that's where the hotter water is rising up, and in the center you have cooler water coming down in to replace the hotter water that's rising through the fluid. By the time you get to 14 seconds, convection is well established on this study. So one of the ways that we minimize the amount of volume that we need to use is through the use of our liquid cell accessory, which allows as little as 2 milliliters to be tested. So after all of that, it's a good idea to validate the performance on a variety of different materials. So this is looking at distilled water, the thermal conductivity of distilled water as a function of temperature, compared with the NIST-JANAF thermophysical tables reference values for that of distilled water for thermal conductivity. This is the same sort of a plot with ethylene glycol. Again, in all cases across the full temperature range, the percent error is less than 5%. This final plot of this is looking at a transformer oil from minus 25 degrees Celsius up to 100 degrees Celsius. And again, in this case, the thermal conductivity testing is always within 5% of the reference value for that material. The next set of validation data I'll illustrate here is tested using a high pressure cell accessory like you see on this slide here. You can see the sensor in the center of the bottom of the cell there. And basically, when you have one of these cells, if you have it equipped for liquids, there's a little cup at the bottom that holds your fluid that you're testing. And you can see the thermal conductivity of a silicone-based heat transfer fluid, Durotherm S, from basically room temperature all the way up to 300 degrees Celsius. We also looked at a slightly different type of transformer oil recently, and this shows the test results from that. So at this point, I'll make a few general conclusions on testing of liquids before I move into some application data generated from some of our clients. Generally speaking, experimenters who are working with longer test times should be skeptical of their data if they're testing on liquids, because you can have that risk of convection. I've seen a few papers in literature which are reporting thermal conductivity on very non-viscous fluids such as, or liquids rather, such as, uh, pentane or acetone, and they're using test times in excess of 30 seconds. And if you're using that long of a test time with a testing a sample with a relatively low uh, viscosity like that, you're running a really significant risk of having convection give a positive bias to your test data. So that's one of the reasons why we developed the 1 second test time on the MTPS sensor to avoid that risk. The second thing to that I should note for people looking at test reports in the literature and trying to evaluate the quality of them is that a good quality research paper looking into thermal properties of fluids should report at the very least the test time, the power applied, the plot of the temperature versus the time, sensor and probe dimensions and designs, as well as if you're deviating from known best practices for fluids testing, a validation experiment with a reference fluid that has a similar viscosity with similar time and power parameters. So all of that said, let's jump into some application data. The first one is from a paper called Enhanced Thermal Conductivity for Nanofluids Containing Silver Nanowire with Different Shapes. So in this case, what was done was the first silver nanowires were synthesized using this process that you see here, where the silver was originally developed from silver nitrate, and then it was reduced into these silver nanowires. And that was done over an oil bath with stirring. In this slide, you can see the two different sizes of nanowires that were generated. So there's the longer nanowires on the left-hand side and the shorter aspect ratio or smaller aspect ratio nanowires on the right-hand side of the screen here. So you can see in both cases, as the concentration of the nanowires as a volume fraction increases, so too does the apparent thermal conductivity. But that effect is larger for the nanowire that has a higher aspect ratio. And the reason for that is that the nanowire can make a more coherent communication network, for want of a better phrase, throughout the fluid matrix, and therefore it will have a more efficient heat transfer. The next set that we'll take a look at is a paper titled Silver Nanowires Contain Nanofluids with Enhanced Optical Absorption and Thermal Transportation Properties. This was published in Energy and Environmental Materials. So similar to the previous paper, this group was looking at using silver nanowires to improve the thermal conductivity of their fluids. And again, they're looking at different lengths of wires being explored. You can see in this case on the left-hand side, the thermal conductivity test data. So as a function of nanowire concentration, you have the thermal conductivity response. And then on the right-hand side of the screen, you can see the relative improvement of the thermal conductivity of the fluid for different lengths of the nanowire. The next application data report we'll take a look at is titled Intriguingly High Thermal Conductivity Increment for Copper Oxide Nanowires Contain Nanofluids with Low Viscosity. So one of the biggest challenges with nanofluids in terms of managing the thermal properties and also the viscosity is that as you add more filler to a fluid, it is going to become more viscous, generally speaking. And so that increase in viscosity poses a real challenge to get it to flow and work effectively as a heat transfer fluid, because primarily the main mechanism that you're going to be transferring heat through if you've got a heat transfer fluid is through the convection or the physical motion of the fluid. So if you want to do that, you need to have a fluid that can flow very well. So that's why low viscosity is really a key target right now in nanofluids, because if you have a nanofluid with a very high effective thermal conductivity, but it doesn't want to flow, you're kind of back at square one. It's no more useful than a lower thermal conductivity, more classical heat transfer fluid like a transformer oil or water even. So in this case, they're using copper oxide because of its high thermal conductivity and low electrical conductivity, that it can be used for situations where the heat transfer fluid needs to be electrically insulating. So in this case, this is some TEM images of the growth of the nanowires, just showing the process that the clients used. And this shows the thermal conductivity test results on this work. You can see in red, there's nanospheres, which were basically being used as a control to study the effect of a large aspect ratio, and versus the nanowires, which are in the dark black squares. On the right-hand side, you can see the thermal conductivity enhancement and the much higher activity of the nanowires as compared with the nanospheres in terms of the enhancement of the thermal conductivity for a given volume fraction of filler addition. Now the last paper we'll take a look at is titled Ultrasonic Preparation, Stability, and Thermal Conductivity of a Capped Copper Methanol Nanofluids. This was also published in Energy and Environmental Materials. So in this case, what the authors did was they capped copper with 3-aminopropyl trimethoxysilane and use that as a filler in a methanol-based nanofluid. So the capping was basically just to make it more lipophilic so that it would dissolve and suspend well in the methanol. The goal here was to achieve improved thermal conductivity without clumping and other issues that some nanofluids are prone to. In this case, you can see the effect of the thermal conductivity enhancement ratio versus the particle loading as a function of the volume percent of particle loading. So that sums up the content for today's webinar. I'll just highlight a couple of upcoming webinars before I stop the recording and get started with the Q&A session. So we have 2 upcoming webinars in early next year. The first one is Thermal Conductivity Applications in Consumer Wearables and Biomedical Technologies. So this is looking at thermal conductivity as it would be applied to things like, a smart watch like the one I have on today, or a portable medical device, those sorts of things. The second one is titled Textile Panel Discussion, International Test Methods and Best Practices in Developing Internal Standards. This is going to be something that my colleague Aria Hakimian is going to be championing, and that will be the week after on Thursday, January 21st. So before I stop the recording, I would like to thank everyone for attending today. I do appreciate that you take your time, an hour out of your day on a busy Thursday in December while everybody's getting ready for the holidays. So it is very much appreciated. Thank you.